These two images show processes that you're probably familiar with. The rusting of iron, which is the reaction between iron and oxygen, and the burning of coal, which is principally carbon, also reacting with oxygen. Now, both of these reactions are exothermic, which means that they release heat as a product of this reaction. Now, you wouldn't be too concerned about reaching over and grabbing this iron chain, even though, as it's rusting, it's slowly releasing heat. But you would be concerned about grabbing one of these red-hot coals here, even though that process involves the reaction of an element, again, with oxygen. And the reason has to do with speed. Iron rusts over a period of tens or hundreds of years, whereas a chunk of coal will burn through in an hour or so. So all that heat gets released fairly quickly. So the difference has to do with speed. Is it slow or is it fast? We chemists want to study the speed of such processes. We call that study chemical kinetics. And we would like to know, is it possible to speed reactions up or slow them down? And why is it that some reactions run fast and some run slow? So chemical kinetics, here's some definitions from your textbook that define what this is. Chemical kinetics is the study of rate of change of concentrations of a substance involved in a chemical reaction. And actually, even though it says concentrations here, really what we're interested in is converting reactants into products, and we want to know how fast does that take place. And really all we care about is the change in amount. And we measure amount in moles. So we really care about the change in number of moles of a reactant or of a product as this process is taking place. Of course, if the volume is staying constant, then we've got a certain number of moles in a given liter or a given amount of space, and so we can use concentration as a proxy for the amount or moles of substance. So reaction rate just tells us how rapidly a reaction occurs. So just like all rates, we're trying to measure something that changes over time. So all rates are changes over time. For example, a change in position over time is just a speed, how fast you're going. So if you drive from where you are to the nearest city, that's a certain amount of distance, and you can divide by the time it takes, and that would be your average rate of travel. Now, sometimes you might actually be going faster than or slower than that average rate of travel, but on average, that tells you your rate of travel. Similarly, for reaction rates, we want to measure how much does a reactant or product concentration, which is telling us about the number of moles, change in a given amount of time. So in lab, we learned about several factors that affect the rates of reaction. We studied the reaction between potassium permanganate, oxalic acid, and sulfuric acid. The potassium permanganate oxidizes the oxalic acid to carbon dioxide and water. And we discovered that if you change the concentration of sulfuric acid, the rate changes. If you change the concentration of oxalic acid, the rate also changes. And interestingly, increasing that concentration seemed to maybe either have no effect or actually slow the reaction down a little bit. We also observed that for that particular reaction, if you increase the temperature, the reaction runs more quickly. And then we saw something interesting, that if you put some unrelated chemical in this case it happened to be copper, well, that particular substance seemed to speed up the reaction. We call that kind of material a catalyst. A catalyst is added to a reaction to speed up the reaction, but is itself not changed in the overall process of the reaction. We did not study physical state of reactants, but that actually comes into play as well. So is the reactant a solid, a liquid, or gas? How much surface area does it have? And so forth. A good example of that is this process. So if we think about a log and we burn it, then that log will burn slowly in a fireplace over time. But if we take that same log and grind it up into sawdust and take that sawdust and ignite it, it will explode, reacting fairly instantaneously to burn all of that wood very quickly. This is actually a hazard in grain silos and grain producing areas. There's a lot of dust around, and sometimes that dust can pick up a spark and then ignite, and you have a very, very big explosion when that happens. So physical state, surface area matters. The issue here with the log is that oxygen is reacting with the cellulose in the log, but only on the surface. So the oxygen can only get onto the surface, and so that happens quickly, burning through the log as the oxygen kind of gets down in between. Whereas in the sawdust, you've got lots of surface area, lots of places for the oxygen to react, and so all that wood reacts very quickly, releases a lot of heat very fast, and really accelerates that reaction, makes it go even faster, and we call that a thermal explosion. Bad news. So let's talk about how you might define quantitatively a reaction rate. So what we do is we're going to need to measure the change in the amount of a reactant or a product, and we're going to divide that by the amount of time it takes for that change to happen. So a given change in time. What are the units on rate going to be? Well, amount of reactant might be measured in moles. That would be the SI unit for amount. And so it might be moles per second. That would be the SI unit. More commonly, though, we can measure we don't count individual moles, we measure a concentration. So in lab situations, often we will measure the amount in terms of molarity, moles per liter, capital M. And so the units on rate will be moles per liter per second. So written like this maybe makes more sense, moles per liter per second, which we can also say, what is moles per liter? Well, that's capital M, molarity, per second. So those would be typical units for reaction rates. But you can use any equivalent measure of amount of stuff, any equivalent concentration unit, and any time. So it can be molarities per hour, or molarities per year, or molarities per minute. Any of those work. You can also measure concentration in different units, like percent or parts per million. So we will use square brackets to represent the concentration, and that will typically be in molarity, moles per liter, of some substance that's inside the square bracket. So inside the square brackets I could put some substance label like O2, and that would represent the molar concentration, or the moles per liter, or just the concentration of oxygen. So let's look at a very specific example. So this is the reaction between nitrogen and oxygen. This is a reaction that takes place in the internal combustion engines of motors, like in your car, and it produces nitrogen monoxide. And this is a component of smog. So it's fairly nasty stuff that we don't want to be around. So this reaction says that 1 mole of nitrogen gas reacts with 1 mole of oxygen gas to produce 2 moles of NO gas. So let's say we wanted to measure the rate of formation of NO gas. What we would do is we would measure the change, so delta here means change, in the amount or concentration of NO, and we would divide by the time it takes for that change to happen. So delta NO divided by delta T. So how would we calculate that directly? Well, we would need to know the final NO concentration at some time that we decide. We're going to subtract from that the initial NO concentration, which might be 0 if we haven't produced any of it yet. And then we're going to calculate the time change between the final and the initial point. And so that's how we would calculate the rate of NO formation. Similarly, we could calculate the rate of N2 consumption. Now you'll notice here there's something interesting. There's a minus sign in front. We will always define rates to be positive. So just like when you're traveling a distance, you don't talk about going negative 30 miles an hour if you're going in reverse, which would be an incredibly insane speed to be going in reverse in. But anyway, you wouldn't say I'm going negative 30 miles an hour. We just say 30 miles an hour, and then you can talk about forwards or backwards or whatever. In the same way, all of our rates of chemical reactions will be expressed as positive numbers. So if we look at delta N2, well, N2 is a reactant, so it's going away. So the amount that we have later will be less than what we start with because it's a reactant. And so delta concentration of N2 right here, this will be itself a negative number because N2 is going away. So we multiply by a minus sign out front to make that positive. But otherwise it's the same, N2 final minus N2 initial divided by the time, the initial time and the final time change. Similarly, we could define the rate of O2 consumption in this way. So these are the rates of production or consumption of any reactant or product, and it gives us a formula that we could use to make some measurement and actually calculate what those rates are. So it's interesting that this reaction we can imagine proceeds at one rate, but the rate of production and the rate of consumption of these different chemicals might very well be different. And that's easy to see if we think about the stoichiometry, right? So as this reaction proceeds, we make 2 moles of NO for every 1 mole of N2 or O2 that are consumed. So NO is being produced twice as fast as N2 or O2 are being consumed. So we often talk about the relative rate of consumptions or consumption of reactants or formation of products, and that's going to be based on the stoichiometry. So we want to compare one rate to another. That's why we talk about relative rates. I kind of like to give an analogy here. So imagine a conveyor belt at a factory. Maybe you're manufacturing cars. So that conveyor belt is running at one speed, just like the reaction is going at a certain rate. But the rate at which you're consuming the pieces that might go into building your car will be different. So as you move down the line, you are consuming tires, for example, at a rate that is different than the rate at which you're consuming steering wheels. Because as the car moves down the line, you put on one steering wheel, but 4 tires. So tires are going to be consumed 4 times as fast as steering wheels as you're building a car. Well, the same idea applies when we're thinking about reaction rates. And what we want is the rate of the reaction. We kind of want the speed of that conveyor belt. How fast is this reaction turning over reactants into products? And so that's defined down here. The rate is minus delta N2 divided by delta T. So that's just the rate at which N2 is consumed, minus delta O2 divided by delta T. That's the rate at which O2 is consumed. And those two are proceeding at exactly the same rate. So they are, in fact, equal. But how does that rate compare to the rate at which N2 is being produced? Well, it's the change in N2 concentration divided by delta T, and then we have to divide by 2 here because the rate at which NO is being produced up here is twice as fast as O2 and N2. So we divide by 2. In general, if we have a reaction that looks like this, little a moles of some chemical A plus little b moles of some chemical B react to produce little c moles of some product, capital C, then we can define rate of reaction. So this is the rate of the conveyor belt. How fast is that reaction going? So the rate of the reaction, it's RXN period there, my abbreviation for reaction, is equal to negative 1 over lowercase a, so we're dividing by lowercase a, times the change in concentration of A divided by delta T. My A disappeared. There it is. And that's going to be equal to negative 1 over lowercase b times the change in concentration of B, how many moles per liter are going away in a given amount of time, divided by delta T. And that would be equal to positive 1 over lowercase c times the change in concentration of C divided by the change in time. So in each case, we're dividing by the stoichiometric coefficient, and remember, for reactants, we make them negative, whereas products are positive. So that's how we can write down a general equation for any reaction. Now let's look at some actual reaction rates. Here's that reaction that we were just studying. N2 plus O2 gives 2NO gas, and here it is represented pictorially. And here's some actual data. So we've measured the time in microseconds, and at each period of time we measure the concentration in micromolar. So micromolar right here, mu is the symbol for micro. That's going to be the number of micromoles, so that's a millionth of a mole per liter that we have. And we're measuring NO concentration in the same micromolar. And so you see that N2 and O2 both start out at 17 micromolar, and as the reaction proceeds, well, they're getting consumed, so that concentration goes down. At the same time, the NO concentration is going up. So here's a plot of that data, concentration versus time. And what you'll see is that the rate at which N2 and O2 is being consumed is not the same all the time. It looks like it kind of slows down. So the N2 and O2 is not going away as fast. So in the same 5-second period, we're losing not much N2 and O2 compared to a 5-second period here at the beginning of the reaction. The same is true for NO. Its rate of production seems to be slowing down. Okay, so let's think about how we might calculate a rate of reaction. So let's say we wanted to calculate the rate of production of NO. So what we do is measure at a particular time the concentration of NO. So right here we've measured that concentration. It's right here at 10 seconds. We know the concentration of NO is 14.8 micromolar. At 5 seconds the concentration was 7.8 micromolar. And then we know those 2 times in microseconds. And so now we can calculate the rate of production of NO. It's the rate of production. So I'm going to write rate prod for production is equal to the change in the concentration of NO. And so that's going to be 14.8, our final concentration, micromolar, minus 7.8 micromolar. And that's going to be divided by the change in time. So 10 seconds minus 5 seconds. And so we'll get our rate in units of micromolar per second. So we just need to take the difference. So we have 14.8 minus 7.8 is 7, divided by 10 minus 5 is 5. So we have 7/5, which is 1.4. And so that would be the rate in going from this point to this point. Now actually that's something that we would call the average rate, because the rate is actually slowing down a little bit in between these 2 points. So we talk about the average rate as the change in concentration of a reactant or product over a specific time interval. So if we had chosen this time interval to be longer, the average rate would have been different. So here we have a 5-second time interval. It would have been different for this 5-second time interval. And if we would have chosen this whole 30 microsecond time interval, it would have been different yet. So we call those average rates. Now we might also be interested in what we call the instantaneous rate, and that's indicated here by this green arrow. So that's the rate of the reaction at any particular instant in time. Here at 2000, this unit is in seconds down here. This is time in seconds. So here at 2000 seconds, we might be interested in what is the rate at which O2 is being consumed. And the way we do that is at a particular point that we're interested in, we draw a little line that is tangent to the curve at that point. So at this point we want to find the line that is tangent to that curve. And I'm going to blow up this region a little bit to show you how we would then calculate that instantaneous rate at this one instant of 2000 seconds. So here's the blow up. So we've drawn our line that's tangent right at this point. So here's our tangent line. And so any 2 points on this line are define the line, and so I'm going to pick 2 points, and to get the slope what I need to calculate is the change in the O2 concentration between these 2 dots that are on my line here. Now realize that those are not actually on my curve. That's okay because we're calculating the instantaneous rate. So we're going to get this rise over this run, delta O2 divided by delta T, and that's how we'd calculate the instantaneous rate. So that's going to be the slope of this line tangent to the curve. And so that's going to be 0.0084 molar minus 0.0072 molar. So that change in concentration divided by the change in time, which would be 3,000 seconds minus 1,000 seconds. And that works out to be 6 times 10 to the negative 7th molarity per second, moles per liter per second. So those of you that are in or have taken some calculus might recognize that what we're doing here is we are finding the value of the first derivative at this point. So if you're taking calculus, you'll know that what we're talking about now relates a little bit to this concept of a derivative. So here's a practice problem. Let's see if we can calculate the average rate of reaction for the time period between 15 microseconds and 30 microseconds using the data below. So here's data again in micromolar, and times are in microseconds. So collect and organize and analyze. So we need an equation in order to calculate this, and so we're going to use our formula that rate of reaction is equal to positive 1 over 2, because that's the stoichiometric coefficient here, times the change in the NO concentration over that time period, divided by delta T. Now, I picked the change in the NO concentration. Why did I do that? Well, actually, no particular reason. I could have looked at the change in N2 or O2 and also calculated the rate of reaction, but my formula might have been different. So I would have had a negative in front, and I wouldn't have had a 2 in the denominator, and the symbols would have been different over here on the right-hand side. But I'm going to use NO. So here's my formula, and do I have the data that I need? Yes, I can calculate the change and I'm trying to find 15 and 30 microseconds, so I need these two rows of data. So I need the change in concentration of NO, so here's the final and initial values, and I need the final and initial times, and there they are. So now I just need to substitute into my problem to substitute in my equation to solve this problem. So I have 1/2, then change in NO concentration, so 26.7 minus 18.6 divided by 30 minus 15. And the numerator is in units of micromolar, and the denominator is in units of microseconds. And so we punch that into our calculator and get 0.54 as our result, 0.54 micromolar per microsecond.